So we are going to start with a diamond review. Now, maybe you've seen the diamonds before, maybe you haven't. This is kind of an intro to factoring that we're going to get into. Because when we're factoring, we need to be able to figure out pairs of numbers that multiply to one value, yet add up those same values to another. So the example I've got here at the top, if I'm looking for two numbers that multiply to 20 and add to 9. 5 times 4 is 20, 5 plus 4 is 9. Those would be my two values. When we start looking at factoring here in a little bit, we'll give you a little more of a stretch of this preview. You may have something, okay, that looks like this algebraically. This would be the algebraic representation of this. So once we get to factoring here in the next couple of days, we're always going to be looking to see, hey, what multiplies to get the number on the end? What adds to get the number in the middle? And so we do it this way just because it's more of a quick visualization. But when we're actually factoring, we'll have two sets of parentheses, two quantities. Whatever our first variable is, in this case it's x squared, which would be x times x. The values that you get here in the sides of your diamonds, a positive 5 and a positive 4, gives me the factored version of this quadratic. Now, I will not make you do this when you're doing these. It is a way of checking, though, as you do them. That's why I'm going to get myself a Post-it here. And that would be to multiply or FOIL this out. Now, again, FOIL. First, outer, inner, we're multiplying on all of these. And last, I always tell people if you do it right, get you a little smiley-faced guy there. So, kind of make sure. Put our like terms together. And if you get the original expression back, you've done it right. Now, I hope we wouldn't have to do that on all of them. Maybe we do it on a couple if we're not sure. But that's how this is going to look. So, on this particular sheet, what we're going to be doing, except for the first one where I tried to kind of give you a little bit of a layup, is do that process. So here, multiplies to 63, adds to 16. I gave you one of the values. 9 plus 7 is 16. 9 times 7 is 63. Like, okay. And we'll just do a couple of these. So I just want to get you kind of thinking. Now, number 2 could be a little more interesting. Multiply to negative 81. Add up to 0. There's always going to be clues in these. And some of you are just dying. You're like, I know. When you're multiplying to a negative, we know something right off the bat. One of the values is going to be positive. One of the values is going to be negative. I don't have an option with that. I also know them adding up to 0. Probably needs to be the same number. So there's always going to be with factoring, because I always have people say, factoring's hard. But if you take all the clues into consideration, it usually makes it a little bit easier. 9 times 9 is 81. A positive times a negative is a negative. And two opposites, 9 and negative 9, would add up to 0. That's all I want you to work on this, just getting the mental math thing going. So I want to do one more, and then we'll kind of do our other little mini discussion here. I'll let you play with these a bit. Multiply to 12, add to negative 7. Again, think about clues. If I'm multiplying to a positive, they could be both positive, they can be both negative. How do I know which one? Look at the sign of the add numbers. If this says negative, these both have to be negative. That's the thought process we're working on. So what multiplies to 12 and adds to 7? 4 and 3. Or 3 and 4. Because again, when we're adding, negative and negative doesn't make positive. Think about money. If I owe my friend $4, I borrow 3 more. Now I owe 7. But negative times negative is positive. So that's the thought process working through with the diamonds, getting us that little intro towards some of the finer details of factoring. Hopefully not too bad of a deal. The other part that's coming here fairly quickly, if we take a flip over. Ooh. Okay, reducing square roots. Now, here's what we're not going to do. When we're reducing square roots, if it were as simple as grabbing a calculator and going, okay, so square root of 48, all right, square root of 48, and writing 6.93 or 6.9, we wouldn't need to do this, but that's not what we're going to do. No decimals. You're like, okay, well, what am I going to do then? Well, what we're going to do is we're going to break these radicals down like we're supposed to mathematically. So, I give for a little bit of assistance a list of values. Not just any list. Not Hardy just making up some random numbers as we go here. There is a method to my madness. I'm trying to see how mad I'm going to have to get here. I don't think I'm going to have to go beyond here. What non-random group of numbers did I just list? What do they have in common? They're all perfect squares. 1 squared, 2 squared, 3 squared, 4 squared, 5, 6, 7, 8, 9, 10, 11, 12. If you looked at that and you're like, I had no clue what those were, we need to start getting used to them. Because there will get to be a point that you're going to need to just know them. So, what are these going to do for me? Well, when we're reducing square roots, we're going to start working again on our mental multiplication. What we're attempting to do with all of these is we're going to break these down into two separate radicals. But here's the catch. One of the two radicals that I break these down into has to be one of these. Because that's where the reducing part's going to come in. Here's the other part. We need to find the largest square factor. It's not just good enough to say, ooh, I found a perfect square that's a factor. Oh no, we're going to take it a step further. We got to find the biggest one. And number 1 is a perfect example of that. So, now that I hopefully have not spooked you too much with this, anybody care to take a stab at which one of these numbers, which of these is the largest value that goes into 48 nicely? $16. So 16 times 3 is 48. I know some of these are larger. I'm not expecting you're going to know factors like 294 off the top of your head. You're going to have to play with them a little. But one of them will break down nicely. And I have this little remembering thing of this to help you a little bit. Okay? I always like to refer to this as radical jail. So, 48's in radical jail. Not doing this very well. 16 is perfect. Because of its perfect behavior, 16 gets out of radical jail with its new identity, 4. Okay, bad math joke incoming. You get extra credit for laughing at this. 3 is still acting irrationally. It's an irrational number. It must stay in radical jail. Well played. Well played. So when we're doing these, unless the value underneath is a perfect square itself, this is what your answers are going to look like. The perfect square breaks down. The irrational value will not. But here's why I said number 1 is a good example of where we can get into trouble. Because a lot of times people will take whatever the easiest square root value is. They'll look at 48 and they'll say, ooh, 4 goes into it. And they'll be like, sweet, 4 and 12. And so they're like, the answer is 2 square root of 12. Now, to be honest, if I go to my calculator and I do 4 times the square root of 3, and I do 2 times the square root of 12, I do get the same value out, it's true. But it's the same thing as when we look at fractions and we say, hey, 2/6 and 1/3, one is more simplified. If I look at 12, I notice something. It still has a perfect square as a factor. It hasn't been simplified as much as it can. So if sometime I break one down and I look and I go, ooh, that still can go further, I would have to do that. I would be like, ooh, so 2, the square root of 4 is 2 square root of 3. And now I've got 2 values that are outside a radical jail that can get together. Do I want to go through all of this to get to the answer? Not really. So I really want to work hard at getting that largest perfect square value out of there so I don't have to do that. And a lot of these on here are purposefully made where you could have multiple options and are going to have to think about it a little bit. Let's see. Let's find one that's not as fun because you're just like, ugh. Here, let's play around with one that's bigger. All right, 252. And then I got one other one we want to look at. Now, the odds of us knowing which one goes into 252 off the top of our head, probably not very good. I'll admit it. I'm even sitting here right now going, what was this one again? I don't remember. Suggestion, if you're going to start playing with these, start with some of the bigger ones. If you're not sure, I mean, maybe you're like, I don't know, does 121 go in? Nope, that didn't work. I got a decimal. And you can kind of play around a little bit. And you're like, do any of these go in? Yes, I swear they all have something. Okay, then. So 36 and 7. So 36 is perfect. 7 is irrational. Break down the perfect. We're good. So the other question that typically will come up with these is, well, what happens if there's a number on the outside? So, like, for instance, let's say number 23. And then I will move myself out of the way here. Okay, we're going to ignore the 5 here momentarily. And just break down the 45. So 45, this one should be a little easier. What's going to be my perfect square that goes into 45? 9. Because 9 times 5 is 45. So that 5 is still going to stay out here. My 9 breaks down. It's perfect. This 5, not so much. And now again, just like we did on our other one that didn't break down completely because we didn't get the largest square, I can multiply those together to get to my simplified form. So like I was saying, this is a little bit of a preview between factoring, breaking down radicals, okay, simplifying radical expressions that we're going to be seeing in this next portion of our course stuff. I just wanted to get you a little bit of background in it. So play with some of these. See how they go.